Hello, I'm Len Malchinsky. Welcome to Examining Overshoot and Collapse with System Dynamics. Let's start with this. What's systems thinking? A couple of fellows, Arnold and Wade, state that if we're going to define systems thinking, we have to manage these three aspects. What's the purpose? What are the elements? And what are the interconnections? Now, I also want to say there are many other definitions of systems thinking, which we'll see in a few minutes, but let's look at what they say. So, a requirement to define systems thinking must say what's its purpose, right? Can we describe it in a way that can be clearly understood? Can we describe the characteristics of the system, the elements? And finally, can we describe the way the elements feed into and relate to each other? Down here at the bottom of the page is the actual citation to the Arnold and Wade paper. Okay, here's more. Barry Richmond, who's the founder of what's now called IC Systems and Stella Architect, said, "It's the art and science of making reliable inferences about behavior by developing an increasingly deep understanding of underlying structure." Peter Senge, a fellow student of J. Forrester and author of the well-known Fifth Discipline, said, "It's a discipline for seeking wholes and a framework for seeing interrelationships rather than things, for seeing patterns rather than snapshots." And finally, Linda Sweeney and John Sterman say, "It's our ability to represent and assess dynamic complexity. For example, behavior arises from the interaction of a system's agents over time. And we represent and assess this complexity both with text and graphics." Another very common way to look at what system dynamics and systems thinking can do is related to this diagram of how we see the world. Most of us see events, things that we can observe, what's happening. Systems thinkers and system dynamicists believe there are patterns of behavior that underlie these events. Underlying the patterns of behavior is the structure of a system which permits certain things to happen and which prevents certain things from happening. And all of this is built upon humans' mental models of what the world is, how it works, what are their values and their assumptions and their beliefs. And this is often called the iceberg model, in reference to the fact that it is often said that most icebergs in the ocean have only 10% of their mass above water and 90% below water. Systems thinkers and system dynamics say if events is all you concentrate on, you're not doing an adequate job of understanding your system. So, we observe events and data. We can identify, hopefully from them, patterns of behavior over time. We can find out what kind of structures might drive those events and patterns. Again, recognize what values and assumptions shape the system. And I should say that's typically done with clients and stakeholders. And then finally, and this is probably the most difficult part, identify optimal choices to alter the patterns that we don't like, the patterns of behavior that we don't like to see happen. Okay? So, a couple of more things about systems. I highly recommend this textbook called Systems 1. It's very small, I think 40 pages. And I know there was some effort going on in Santiago at one time to translate this to Spanish. But Draper Kaufman has this very nice picture of a cow, and he says, if you divide a cow in half, that doesn't give you two smaller cows. So systems can't be divided and still be systems, right? It doesn't matter how the parts are arranged. If it doesn't matter, then it's not a system. It's what Draper Kaufman calls a heap, a pile. Another difference is you can't really change a heap by adding to it or taking away from it. Imagine a pile of maize or sand or something like that. And finally, when we say that a system functions as a whole, its behavior depends on everything in the structure, not just adding up separable behaviors of different separated pieces. Okay, some more foundations. We believe as systems thinkers and system dynamicists that the structure of the system generates behavior. And what that means is it's not autonomous, but the structure both permits and constrains certain behaviors. The dynamics of a system interact because of physics, the laws of physics, the availability of information, the decision rules that we've implemented. Those rules could be automated, or those rules could be implemented by humans. Mental models count a lot. Just about everything we do in life is based upon a mental model. It's not enough to change just physical structures, information, and incentives. We have to work on mental models. And then the last thing here, systems thinkers talk about this fundamental attribution error. Basically, don't blame problems and behavior that you don't like on people. It's typically not the people. It's typically the system, which is, again, based upon the physics, the information availability, and the decision rules. Now I'm going to make a rapid jump from systems thinking to system dynamics. But before I do, you all know systems can get quite complex. And therefore, in the 1950s, a fellow by the name of J. Forrester developed a methodology to apply systems thinking and the understanding of systems using modeling and computer simulations. Because Jay believed that after a very short description of a system, it gets so complex that our minds cannot comprehend nor improve them. We need to build a simulation. How do we do that? Well, those simulations are composed of what are called rates and levels. And you see in the diagram here the phrase hydraulic metaphor. Sometimes this is simply called a bathtub metaphor. This cartoon valve and this valve are showing rates. This one is showing inflow of water into the bathtub. This is a rate that shows outflow. The level is the bathtub itself. So imagine you're doing this in the real world and you have a clear plastic bathtub. And water is flowing in and water is flowing out, and you take a photograph. From that photograph, you should be able to estimate how much water is in the tub. At a minimum, you should be able to estimate the height of the water. But you cannot estimate the rate at which water is flowing in and the rate at which water is flowing out. That's how we distinguish a rate from a level. using the snapshot test. If we were to take this physical depiction, and put it into a piece of software called VenSim, the picture would look something like this. We have an inflow into a stock, and we have an outflow. One important thing that's here explicitly, but not here, we don't know, nor do we care where the water is coming from. In this system, the system could be expanded to the left. So look at that. On the right, we don't care where the water is going. Of course, we could expand our system to include that too. So what we've got in the stock, the computer software is doing what's called integration, calculus integration. It's summing from some starting time to an ending time all of the water inflow minus the outflow plus the starting level. That describes the stock mathematically. And then inflow and outflow are described by a differential, sometimes just a difference equation. And that is the change in the stock for a specific slice of time is simply the inflow minus the outflow. That's the change. The amount of water in the stock is here. Okay? Keep going. So, levels or stocks, those are the elements that you can see, feel, count, or measure. It's sort of a memory. It's the present memory of the system, and it's the memory of everything that's happened to that stock in that system at any point in time. Stocks typically change slowly. They often act as delays or lags or buffers or balance, just some words that people often use, and sources of momentum in a system. And finally, stocks, especially large ones, respond to change even if the change is sudden, typically by only a gradual filling or emptying. If the volume in your stock is so many times greater relatively than the rate of inflow minus the rate of outflow, you don't see rapid change. This is something that systems thinkers and system dynamicists truly believe, that most of us tend to ignore delay. As humans, we expect instantaneous response, and in the real world, it usually does not happen. Let's move forward. Okay. In systems, both systems thinking and systems dynamics models, we talk about feedback. Here's a very simple, generic system. This is in the newer version of VenSim, which has a little bit different symbol set. Here is a stock or a level, and here is a rate. And notice that for this rate, something is flowing in. And the photograph here is a metaphor for this simulation and this mathematics. This person is trying to fill a container with water. Will they succeed? Well, here's what's going on. This is what we believe, at least, is going on. The state of the system is the current level of water in this container. The change in the state is this water flowing in. The decision is this hand on this lever to adjust the rate of flow of the water. And the desired state we can't see in this photograph. That's in the mind of the person filling the container. They're using their eyes, and what a friend of mine calls their protein computer to decide, when should I stop? When should I make the decision to turn off this valve and therefore stop water flowing at this point? Now, even when they turn the valve, this amount of water will still drop into the glass, but that's off the diagram. The desired state, is in the mind of the person filling the glass. And that concept is called feedback. They see the state of the system, right? They compare it to the desired state, and then they make a decision. That's feedback. Another silly example, I once worked in a very old building that was going to be torn down, probably not repaired, and when you walked along the floor made strange sounds. And sometimes I wondered, should I take another step? What feedback was my mind getting as my foot touched the floor? Was the floor solid? And should I take another step? That's feedback. Okay? So our action or decisions will eventually change the state, the things we can see. And again, I'm reiterating, it's based upon the perceived state of the system. So those of you who have children, this is always something fun to do, probably out of doors. Try to get them to fill a plastic container or a cup with water from another plastic container. I'm saying plastic for safety. Maybe make a little mark on the glass and see if they can, or cup, and see if they can fill it with water. And they will probably succeed. Now, empty the cup and put a blindfold, put a bandana around their eyes, and ask them to do the same thing. This is why you want to do this out of doors. You have now cut off the feedback. They cannot see the cup filling. Maybe they can tell how full the cup is from sound, possibly from the weight, but I believe, and when I've done this, it's using your eyes that is the best for feedback. And by eliminating that feedback, the cup either doesn't get filled at all or it overflows. Okay? So, now we're going to take all of this, I know this is going very quickly, and say, I looked at the world, I examined the world, I see it's a complex system. I'd like to do something, I'm going to build a simulation model. Models typically have these features. Some kind of schematic, some kind of diagram that describes the system. Many years ago, as late as the 1970s, most of these diagrams were drawn on paper, and the computer software was simply a listing of equations. You'll see in a few minutes that's no longer true. On our diagram, we will see the key variables, the variables that we, working with our clients and stakeholders, think are important. We will draw a stock and flow diagram, like we saw on the previous slide. We will show links of how some variables are linked together and how some are not. We will see feedback loops. We will be able also to see a set of formulas, the mathematics, although most of the modern softwares don't require you to do any of the calculus, just some simple algebra. Okay? When we run the simulation, it will show the behavior, maybe that should be behaviors, of the system over time. Some people are saying that simulation is truly the third branch of science. The first is theory, hypotheses, what we make up in our minds after observing the world. The second is experiments or experimentation. And the third branch of science is simulation. Okay? When we're doing simulation, we're building models, right? Not mental models, but computer models. And I really like this fellow's diagram. He says when we're using models or building models of systems, many of them are for very routine kinds of things. For example, calculating the payroll for a company, calculating the bill that you pay to your power utility, doing simple things that are very, very well defined. The algorithms are very, very well defined. On the other side of the spectrum, there are systems and problems where there's a lot of human interaction. And these two triangles are his way of showing the relative amount of human interaction versus routine. And he says, Michael Pidd, that you can automate a lot of this, but here you really can't automate it. Somehow you have to be able to represent in your model the insights from your discoveries so that people can debate whether you've done it well or not. Another way to add labels to this spectrum, this range, is to say that things on this side are simple puzzles. And puzzles, of course, given enough time, can be solved. And messes and wicked problems take a lot of time. I'm going to reset this. And this is what I believe. Sorry, my animation is a little too fast. That system dynamics handles from about here to here. It actually goes beyond messes and wicked problems. Okay. So you can take several semesters, several years, or maybe a lifetime to become a true system dynamics modeling expert. Jay Forrester, the fellow who developed this World 5 model that was later used in world dynamics and the very famous book Limits to Growth. When he was in his 90s, 90 years old, someone asked him what his profession was. And he said he was a student of system dynamics, the technique that he had invented. So here's just a small piece of Forrester's World 5 model. Now, this is what's called a causal loop diagram. This is not a running simulation. This is us putting ideas on paper with some rules, of course. We have rules on how we do this. Okay. So we take pairs of variables that we've identified and we ask questions. Are these variables, this pair, let's say birth rate and population, is it causally related? Not correlation, not statistical correlation, but causation. If the birth rate were to increase, all other variables constant, what would happen to population? And in this diagram, it's showing that if birth rate were to increase, it supports an increase in population. Therefore, population would also increase. So if birth rate goes up, population, the S stands for same, moves in the same direction, it goes up. Some people say supporting or opposite, same or opposite. Some diagrams don't use S and O, they use plus or minus. If you find that two variables are not causally related, you set them aside. Don't worry about it. If we look at the small diagram here, we see that birth rate and death rate have no link, no causal link. If birth rate goes up, I cannot think of a causal relationship for death rate. Give you a moment to think about that. Okay? And then the last thing we do is, if we find a relationship, we pause and say, is there a delay? Are these things instantaneous? How quickly does the other variable respond? My favorite example of that one is growing food and the food supply. If we are to grow more food, the growth rate, or the number of hectares planted, goes up. We don't get an instantaneous response in the stock of food. We must wait for the growing season to complete. We must harvest and store that food. Okay? Once we do that, now we've got a whole series of loops, and we have our mental estimation of causation. Not only causation, but the direction. So we take a loop and we try to simulate it. We try to take this paper and mental thinking and get it into a piece of software. So let's look at those two variables, population and birth rate. We're going to start a model very slowly with pairs of variables and try to model it. And here we go. The birth rate, and I'm not 100% happy with these names, but that's okay. Remember, you don't learn system dynamics in a matter of hours. It takes time. Birth rate, the arrow is going in, so population will increase. As population increases, it will increase the number of births, which is truly increasing the birth rate. So I've got a feedback loop. Here, the R means it's reinforcing. If this one goes up, that one goes up. If this one goes up, that one goes up. That's reinforcing loop one. This little cartoon is supposed to be a snowball rolling downhill. Some people use that to describe reinforcement in a feedback loop. Okay. If you build this model in software, wow, not only do you have to understand the problem you're dealing with, but now you have to learn some software syntax. How to use that tool. What button do I push? Where should my mouse go? How do I define things? How do I link things? And that takes time. And that knowledge is going to occupy some space in your memory, which is already quite full. The other thing that's good to do is to follow best practice. The best practices exist for many, many reasons. The primary reason is to make you a better modeler. Right? If you develop a process of modeling, you just get better and better. It also allows you to deal with your clients in a more professional way. It also might lead to further work. You'll develop a reputation because you followed best practices. And you'll also find that modeling becomes easier as you develop habits. So, Jorge asked me to think about this, and in preparation, in the back of my mind, to think about the Sustainable Development Goals developed by the United Nations. And you know, or maybe you don't know, there are 17 of them. And these are tough problems. These are messes or wicked problems. These are not routine issues like calculating this week's paycheck, right? Therefore, system dynamics modeling might be a good methodology to, first of all, help me to understand any one of these, and second, make proposals, policies that might help us achieve the goal for any one of these. So I took a good look at them, and believe me, I have seen system dynamics models dealing with every single one of these topics. Large models, and by large I mean thousands of variables, not two, millions of pieces of data, geographic specificity by country, by state, by county, by arrondissement, by whatever political boundary you'd like to use. Very sophisticated models and very sophisticated user interfaces so that non-modelers can use the model to gain understanding and see the results of policy change. So what I did in my head is I said, I can't do all this quickly for the summer school that you're holding, so I'm going to concentrate on one of them, and I'm going to use a very famous small sample model. And the one I picked was life on land. That category of development goal and a problem related to it, or a problem that would fit in that box, life on land. So here we go. Do a simple model, and actually this is quite famous. I'm sure Jorge can direct you to some papers on it. It's got 3 stocks, 3 bathtubs, deer, food that the deer eat, and predators. And the food of a predator is a deer. Okay? And I realize here I forgot to change this slide. It should say, predators prey on deer. Deer are limited by food. Food production is limited by food consumption and the surface area. I apologize. I tried to change the model. I didn't like what I did, and I went back to the original idea. So let's take a quick look. And then what I'm going to do is open some software to show it to you. So here is the full model. It's called the Kaibab Plateau model. The Kaibab Plateau is a physical place in the United States that's near what's called the Four Corners, where 4 political states, Colorado, Utah, Arizona, and Nuevo Mexico, where they all meet. And if you ever get to visit there, there's a place where you can put 2 of your hands in 2 of the states and each of your feet in another state. So your body is literally touching all 4 states at the same time. Okay, so here are my stocks: a stock of deer, a stock of food, and a stock of predators. Okay. It doesn't really matter who these are. I think in the original work they were wolves. Let's take a look at deer. There's a way to increase deer, and there's a way to decrease deer. If we follow the connections, right, the causal connections for deer increase, wow, we see a simple population model here. And we see if we trace this, oh my gosh, the increase in deer is eventually dependent upon food. Well, what increases food? The regeneration rate. What increases or decreases food, it's the consumption of that food by the deer. So notice that that's related. Okay? There's a delay here. It takes time to grow this food. And this is in nature. This isn't human-produced food. There is a maximum amount of food that can be produced without any human intervention. And that's based on scientific historical studies of the biomass in that area. Let's move over to predators. Predators can increase and predators can decrease. I don't have any decrease of predators due to disease or old age. The only thing that decreases predators is hunting. And there's a fraction of them that are hunted each year. And then here, how are deer and predators related? Well, each predator tries to catch a deer for dinner. And imagine you're a predator. If there are a lot of deer, if everywhere you turn you see a deer, great, you're going to eat well tonight. But if the density of deer is quite low, you're not going to do too well, right? So that has to do here with the deer density, and then how many deers are typically killed per predator. Okay? Let's go forward. I'm calling this simple. Maybe that's a mistake. For me, it's simple. I guess I've been doing this too long. Okay? There are real-world limits here on certain numbers like area, the normal amount of food that deer consume, the maximum amount of food, and then how many calories do deer get per acre, per surface area. What's sort of the productivity? Okay. Can such a model based upon an actual place help us to learn? Good question. Can the concepts in such a model then be extended to the sustainable development category, sustainable development goal number 15, the land? So what I'm going to do now is I'm going to end this slideshow, minimize this, and bring this model up in a tool called VenSim. This happens to be VenSim Professional. I can send everyone this model, or Jorge can get it to you. VenSim has a nice feature where I can show degrees of complexity here. So at the simplest level, I've got the 3 stocks, which you all now know. Each stock is able to be increased and decreased. And if I do this, I can add another level. So here now I'm slowly adding things that have to do with deer increase, which is based completely on food. The modeler has determined that's enough. That's enough causality for me to understand deer increase. I'll go down another level. Now I'm looking at food regeneration. So I built that part of the model. Now I'm adding the deer predation rate based upon the number of predators. And actually, as predators eat deer, they tend to have more predator babies. They do better. You go down one more level, and now I've got the predator harvest per year. And if you recall, I believe that is the entire model. If I were building this on my own, without doing this in our little seminar here, I would get this stuff first. I would do this first. then I might add food next or predators next. But I would not, for any reason, put all of these things on the screen at once, because that's not good practice. So I'm going to back up again and go to the equation editor. Again, please don't try to memorize this. And I'm just going to click on deer. And it's going to bring me up a relatively sophisticated screen. Asking me what's the name? Deer. What kind of a variable is it? It's a level. And these are all the kinds in Vensim. Don't worry about that. A level is like a bathtub. What kind of units am I measuring the things in this bathtub? Well, I'm calling those units deer. And my initial value is 4,000 deer. And how does that stock of deer behave? Well, it's the net increase in deer minus the predation rate. Let me move this over. So that bathtub changes by putting deer in and taking deer out. All right. I can check to see if my syntax is correct. It's okay. So I hit OK. And I could do the same thing for predators and find out that their unit is called predators. There's 160 of them. I can do the same thing with food, which is measured in calories, but its initial value is the area times the productivity in calories per acre. And this one is simply the regeneration rate minus the consumption rate. Okay, everybody with me? I'm going to add one more level and take a look at deer increase. Again, this one is called an auxiliary in Vensim. Some other software tools, and I'll show you one other, call it a rate or a flow. This is always measured in units per unit of time. So this rate is deer per year, and it's described as the number of deer times the fractional increase in deer. Well, that's interesting. I'm going to go look at deer fractional increase. And it says deer fractional increase is an auxiliary, but it's a lookup. It's a lookup. Wow, what are all these numbers? So I can go look at that as a graphic. And basically what it's saying is, as the quantity of food per deer increases, the reproductive rate of deer increases. Okay, in this case, it actually starts at 0. So if there's no food for any deer to eat, that's going to have a negative effect on deer births. And the food has to get up to, the food to deer ratio has to get up to 0.8 in order to keep the deer net increase at 0. And if the food ratio exceeds 0.8, the fractional birth rate starts to grow. We're also showing that it never grows above 0.2, which is 20%, a 20% increase in deer per year. And you might be asking yourself, oh my gosh, where did all these numbers come from? Scientists doing real-world studies physically on the Kaibab Plateau, gathering data over many, many years. Okay? So I went to fractional increase, which is not a rate, it's just an extra variable, an auxiliary. Just to be fair, I want to click on calories per acre just to show that it is a constant. It's not determined by any formula. Okay, that's it. All right, I'm going to minimize this one and show the same model in another software, which is called PowerSim Studio. And if you are to start on a system dynamics career, in a very short period of time, you will see, wow, I don't know Studio, but this looks very familiar. I see what I think are stocks or levels, predators, food, and I have to say each of these softwares behaves differently. It can get you the same results, of course, because they're doing the same thing, but the behavior, the mouse clicks, what buttons are available, are quite different. They all implement the system dynamics methodology, though. And you notice there are different symbols here. That's just a feature of Studio. And so here, instead of hitting an equation, I just click on this and I see that my dir in this case is initial dir. It's based on a separate variable. I don't have the number 4000. I have it here, which is one of the modeling best practices, by the way. Any stock or level whose initial value is not 0, we suggest that you create another variable to initialize your stock, to basically fill the bathtub before the model starts running. Okay? And that's why, let me do a zoom very quickly here. That's why you hopefully can see that these lines have dashes, because they're not involved in calculation except at the start. They are initializers. This value is calculated only one time when you start the model running. After that, it stays constant. That's just their way of showing that. Okay? I just wanted to show you that. Very, very quickly after starting on a journey like this, you will see, hey, I understand this completely. I don't know what buttons to click yet, but I understand it. I understand the layout. I know what's a level. I know what the rates are. I know what auxiliaries are. I might not know that these folks use special variable for constant. Okay, let's go back to PowerPoint. That's one of my favorite bands from the 1960s, by the way. Maybe I give extra credit to anybody who can tell me who they are. Okay, let's go back. So here are some results from that model. And what I did, and this is the PowerSim Studio results because that's my preferred software, I changed the predator harvest rate to 20%. So 20% of the wolves will be killed every year. And the deer are going along quite well at about 4,000. And I start harvesting the predators, and oh my gosh, the deer population rises more than 20 times as many, and then it collapses. Overshoot the resources available, which are food, and then it collapses. Predators, I started harvesting them here. They eventually get almost to 0. Remember, I'm doing 20% of what's there, so that it will never get to 0. Food goes way, way down until the point where there are very, very few deer and the food starts to recover. I'm going to do this live in just a minute or two. So here I harvested 10% of the predators instead of 20. And things are looking pretty good. Oh no, I got collapse, overshoot and collapse of the food resource again with predator harvest at 10%. And you note here, the predators are getting really fat. There are a lot of deer to eat. When the deer collapse, the predators collapse. When the deer grow to unbelievable numbers here, almost 70,000, the food resource collapses. And then finally, here's one with a 5% predator harvest. The deer are at 4,000, they get up to about 10. Notice here they're about 70, here almost 90,000. Predators are constant, they start to decline, but then they start to recover because there are more deer to eat. Food, and I didn't put a 0 here, food declines, but the relative scale here is much tighter than here or here. I want to go back and say one thing. This was a real world situation. What people noticed is the deer were disappearing. The food was disappearing because the government said, go out and kill those predators. It turns out that the predators were keeping the ecosystem, the sustainable goal, in balance. Okay? Let me come quickly out of the slideshow and go back to PowerSim Studio. And I will just grab a graph here, put it on the screen, and I'm going to throw deer on it. I think, yeah, and predators. And then just run the model. And because the scales are different, you can see predators here stay close to 0, 160, remember? At the start, deer started at 4,000. Killing off those predators, the deer are reproducing madly. They exhaust the food supply and decline. So, can I play a game with fraction harvested per year? I'm going to open this up. Oh, I've got a time series here. Basically what I'm saying is, starting in the year 1900, I don't kill any predators. I don't kill any. 1905, 1910, I kill off 20%. Let's try to change that to 10%. There are better ways to do this, but I'll try to do this quickly. Again, we can arrange with Jorge if you'd like to play with these models. They are both small enough that they will run in the free versions of both of the softwares. So I cut the fraction harvested from 20% to 10%. I run the model. Oh my gosh, the same thing happened. And we saw that in the earlier example. I can open this up again, and this will be the last time. I'm going to go to 1%. Primarily because I can type that very quickly. Even a person like me who can't type. Reset the model. Imagine, what do you think will happen? What do you think will happen? I lowered the predation rate, started at 20%. We tried 10%, now it's down to 1%. Oh my gosh. Deer start to increase and then come back down. This is running for 50 years. Well, here's the wonder of simulation. Remember the third branch of science? I don't have time to go and talk to these deer or wait for 100 years to pass. So I'll go to the year 2000 and run the model again. And look what happens. There's a natural system here. Predators are harvested at 10%. Deer start to increase. They start to reach a level where they're hurting the food. Geez, can I throw food on there? I don't think so because the units are so large. But let's just put a food graph. How is food behaving over this time period? It's doing the same thing. It's oscillating. Okay? This is to me, one of the wonderful things about simulation in general, and number two, system dynamic simulation and its ability to help me to understand these complex problems, which now hopefully help me to understand that sustainable development goal. Let me go back to PowerPoint and wrap this up. So we saw some of the results. There's that 20, there's the 10, there's the 5 again. And here is a run out to the year 2020, maybe only to 2000, sorry. There's predator harvest. I still get overshoot because the harvest rate is too high. So now you ask your stakeholders, what are your management objectives? Is your objective truly to get this line to get flatter? Can I test policies to make that happen? How should I control the deer population? Should I control the predators directly? This first one means, should I also hunt deer, not just hunt predators? Should I do it to both? Can we optimize? Depending on the software, if you can give it a function to optimize, the software will do it. What time period are these managers and the public thinking about? 5 years, 10 years? Or the politician period of 4 years? I don't know. Are there variables missing from this problem? And what about variation in the values over time? Can I test that? Yes, I can with simulation. And finally, the question all modelers should ask themselves, was this model useful? Did it help people to understand in this tiny little model about a piece of land somewhere in the southwestern United States, simplified, is it helping me to understand conceptually a sustainable development goal? My conclusions: the model was simple, at least from my point of view. 3 stocks, 6 rates or flows, 4 constants, 8 auxiliaries. Let's see, 3 plus 6 is 9, 9 and 4 is 13, plus 8, 21 variables in the Vensim version. We may have seen behavior that was unexpected. We changed some of the constants to try to achieve a goal, and you saw that was difficult. So now, imagine understanding all the sustainability development goals for the world and how difficult that might be. And my claim is we can do that with system dynamics modeling. We can't do it instantly. We can't build one model to solve all the SDGs. The same model won't be useful in every geography, but I truly believe it can be done. Thank you all for listening. Jorge knows how to find me. As I typically say to my students, model on.